Hello everyone, my name is Shanil, and I'm here to present to you my Active 458 thesis which I have completed this semester. The brief outline about today's presentation is as follows. The topic obviously is active filter design and compensator analysis using non-active power theory. The outline will be discussing or giving you a brief introduction, the problems and issues caused by poor power quality, and the mitigation techniques that are in place to improve the power quality. One of the techniques that is used is using shunt active filter, and in order to understand how shunt active filter works and the compensating current that gets generated, the reason why we have shunt compensating current, one has to understand about instantaneous power theory, instantaneous non-active and active power theory, and then followed by the design of active filter, and then the control mechanism, because in order for the active filter to generate compensating current, it needs its IGBTs to be controlled in such a manner so that the compensating currents are right in what's desired. And then we'll be talking about the simulation results about a nonlinear load that was connected to a three-phase supply, got simulated and connected by a shunt active filter, and how the waveforms changed, and calculating the total harmonic distortion percentage, and then finally the conclusion. So electricity happens to be one of the essential items that's being used all over the world, but depending on the load it services, it varies. When we talk about loads, there are two kinds of loads. One is a linear load and other is a non-linear load. In the olden days, power quality wasn't a big issue because most of the loads connected to the power system used to be linear. Hence, the current that was being drawn by these linear loads were sinusoidal and used to be in phase with the load, or in phase with the supply voltage, so power quality was not an issue. But for the past decade, the number of non-linear loads that are being used on our power system has significantly increased. And these non-linear loads, such as arc furnace, air conditioning units, washing machine, computers, they are these non-linear loads, due to their nature, when it draws current from the supply, it draws non-sinusoidal form of current, and this non-sinusoidal form is due to harmonics that are present in those currents. So that is the reason why these non-linear loads, this is the problem non-linear loads are causing, and we need to mitigate these harmonics. Some of the factors listed here is the reason why it's not so good, the harmonics. So it lowers the power factor, there's voltage deregulation, overheating of equipment, causes interference with the communication system, and overall the power efficiency, it kind of reduces our power efficiency. So that's the reason we need to reduce harmonics so that we don't have those problems. And over the years, developers and engineers, they have come up with some of the techniques in which we can reduce those harmonics. These techniques are such as filtering, and in filtering we have passive filtering, active filtering, hybrid filtering, which is combination of passive and active. We can have current limiting devices such as line reactors. We can have isolation transformers. However, for this project, one of those mitigation techniques, that's using active filter has been the major focus. So we'll be studying more about the active filter, how it's implemented and how it generates those compensating current to mitigate harmonics. That's the focus of this presentation and the thesis. Active filters, when they get connected to the power system to reduce harmonics, it has got two kinds of configuration in which it gets connected. One is in parallel with the load, and other one is in series. Series, it just connects in series between the power supply and the load. In between we have like in series active filter gets connected. Over here we can see there is a diagram which shows the shunt active filter, one that's connected in parallel with the load. And these loads here, we can say or assume these are motors, and these motors are being fed from the supply, and obviously they are non-linear loads, so the current that flows is heavily distorted. And in order for us to compensate those distorted current, we are using this shunt active filter, which is made up of 6 IGBTs. It is a 3-phase active filter, and in between we have coupling inductors. So that's like a brief description as to how the active filter works. But in order to really understand what it does and why it gives you those compensating current, understanding about instantaneous power theory is very important. Let's say we have the voltage supply as VA, VB and VC, and we have got the load current as ILA, ILB, ILC. From those two components, the individual phase A, phase B, phase C, we are able to calculate the instantaneous power by simply taking VA voltage, multiplying it with IA current, and then VB voltage, then IB current, and VC voltage, VIC current. That's how we get the instantaneous power. Once we are able to get the instantaneous power, just finding the average of that, we need to get the average power, and the way we can get the average power is using this mathematical formula, this integral of instantaneous power between 0 and the period. We are able to get the average power. Hence, once we get the average power, and the reason why we are finding the average power of that system is so that we can calculate, or we can get the active, instantaneous active current that's flowing in the system. This instantaneous active current is part of the current that's being supplied from the utility to the load. Hence, when we remove this active current from the supply current, we are left with non-active component of the current. So this idea basically means that the supply current, when nonlinear loads get connected to the main system or the utility, and it's drawing current from the supply, those current consist of two components, which is active current and non-active current. This non-active current does not do any necessary work and is the one that contains harmonic, and that's the one that needs to be mitigated or removed, so that we have got the active current, and that active current is the one that does the actual work. Hence, now to remove those non-active components, we use the shunt active filter. The active filter, it generates those non-active components of the current, same as the active current and non-active current that flows in the system. The purpose of this active filter is to generate that same current the non-active current, same magnitude, but 180 degrees phase shift, so that, for example, if the current non-active is plus, this is minus, these two, when they connect, it cancels it off. So basically we are cancelling the non-active current that flows in the system through using this active filter. In here we are showing you the design of the active filter. Active filter is nothing but just made up of IGBTs. It's an inverter. It's either used as a voltage source inverter or current source inverter. In a three-phase, it's made up of 6 IGBTs. As you can see in the diagram, it has got from the 3 legs via the inductors, it goes to the PCC. PCC is just point of connection, is the place where the shunt active filter gets connected to the main system. Since it's made up of 6 IGBTs, those 6 IGBTs, they obviously have a gate signal. They require a gate signal, and that's how it opens and closes and controls the current that flows. There are several control methods that are used to control the switching of those gates, and the control method that is being used in this thesis is instantaneous active and non-active power theory. In the instantaneous active and non-active power theory, we calculate the reference current, and these reference currents are given by these formulas here. And once we are able to get the reference current, it gets compared with the actual current, and the output goes to the hysteresis band, and this hysteresis band gives you a output which is able to control the gates of the IGBTs to generate those generate the compensating current. In the results, as you can see on the screen, we have got instantaneous. There is the load that was simulated was a rectifier, fully controlled rectifier, and there's 3-phase supply. As you can see on the left hand side, there is the topmost is the sinusoidal voltage supply, the middle one is the supply current, and the bottom one is the load current. So this is before being compensated. Then using the same in compensator that gets compensated, we have got the supply voltage followed by the supply current, which has become sinusoidal, and then the load current, which is still the same. So we can definitely say that the active filter does work. And then here it proves using the fast Fourier transformation. Before it was compensated, it was 24%, and once using the active filter it gets compensated, it reduces to 1.04%. So using the instantaneous active power theory to calculate the reference current and getting compared it with the supply current does surely mitigate harmonics or removes the non-active component. In conclusion, I'd like to give the instantaneous power theory is an appropriate field of study for active filter implementation. It has been applied to different cases, the different loads. The line impedance has been varied, and yet we are able to compensate those harmonics in the system and get the real active current from the supply. So basically, using of active filter has been effective, and that is proven through simulation in the MATLAB. For the future work, we can say that active filter at the moment is pretty expensive to implement and compared to passive filters. However, in future, if some designs can come up and active filter can be sold for cheaper rates. That would be a future goal. And also at the moment there are a lot of other harmonics or frequency that get generated by the switching of the IGBTs, and that's something that needs to be worked on to fix the issue. Thank you for listening, and